All right, so I'm not going to prove the inverse function theorem today. That might be done in the next lecture, or maybe it'll take 2 lectures. But let's just look at the statement, and I also want to show you that it's something you've possibly seen before. So here's what it says. So assume you have a C1 function, so it has to be continuously differentiable on some open subset of Rn, and notice that this n and this n match. So what I'm saying here is that f is a function of n variables and it has n outputs. That's needed to make the derivative sort of a linear map from a vector space of one dimension to a vector space of the same dimension, from Rn to Rn. Okay, so assume you've got this continuously differentiable map, and suppose you have this one point in the domain, A, where f prime of A, this linear map, so this is a linear map Rn to Rn, is invertible, so it's a bijective linear map. Then here's what the inverse function theorem says. So here's how I think about this. Is the derivative of f at A is a linear approximation to f near A. So it tells you about the values of f, the values that f takes near A to first order, with this like remainder term that goes to 0 quickly. If that linear approximation is invertible, then it doesn't tell you that f is invertible. It does not tell you that f is bijective, but it tells you that f is locally invertible. So here's the conclusion. Then there is some neighborhood. There is some open neighborhood, U, of A. All I mean by neighborhood, by the way, is neighborhood of A is just that it's an open set that contains A. So there's some open neighborhood U of A such that a few things happen. First, if you look at the image of U, then that's open. And let me just give that a name, V, so I can keep referring to it. This is an open set. That does not normally happen, right? If you just know that f is continuous, for example, so here we know f is continuously differentiable on all of E. So f is definitely continuous, at least. That does not tell you necessarily that f is an open map. It doesn't tell you that it takes open sets to open sets. It tells you that the preimage of an open set under f is open. So this is already something special here. And the next, this is that locally invertible idea that I was saying. If you restrict f to U, then this is injective. This is one-to-one. And so f becomes bijective mapping from the open set U to the open set V. And finally, if you take f restricted to U, which is now a bijection from U to V, and you take the inverse, which you can because it's a bijective function, then that inverse function is in fact a C1 function. So it's a C1 function from V to Rn, to U, really. So that's the inverse function theorem. And again, the way I think about it is that it's saying if the linear approximation to f is invertible, then f is locally invertible. So let's just think about what this would mean in one dimension, where it's actually a possibly a familiar fact. So up there, f is from Rn to Rn, but suppose n is 1. Then f is a function of one variable with just one component. So then it's something that you can plot, maybe like this. Then what does it mean to say, so, okay, let's just focus in on a point, like A here. Then what does it mean to say that f prime of a is an invertible linear map. So f prime of a will be something from a linear map from R to R, right? What does it mean for a linear map from R to R to be invertible? Well, linear maps from R to R are in correspondence with just real numbers. And the correspondence is that a linear map from R to R has the effect of just scaling by some number. And that's the number that we say it corresponds to. So when is a linear map from R to R invertible? Well, when it's scaling by something non-zero, because then you can undo that, right? You can divide. If you're multiplying by a non-zero thing, you can undo that by dividing by that thing. So to say that f prime of a is invertible is basically to say that the slope is non-zero. So here at a, it looks like the slope is not zero. And so we are in a situation where f prime a is an invertible linear map. And do you think that f is injective near to a? Yes, it certainly appears to be so. Not globally, right? There are many examples of f not being injective, right? Like here and stuff. But if you restrict your view to a small enough neighborhood of a, and only focus on there, so just look there and ignore everything else, then the white line here does appear to be definitely the graph of an injective function. So the inverse function theorem is also saying that the neighborhood can be arranged so that its image, which looks like it would be something like this set here. So this would be our U, and this would be our V. It can be arranged so that the image V is also an open set. And finally, also the inverse, if you write down the inverse function, so you've got a bijection here, if you write down the inverse function, then also that will be a continuously differentiable function. So in one dimension, the inverse function theorem is very easy to see what it's saying. And I hope you can also see that if you focus on a place where the derivative linear map is not invertible, like say here, if this were your a instead, then yeah, no matter how close you zoom in to this point, you're never going to see something that looks injective, right? It will always look non-injective. It will always look non-injective. Okay, so here I'm looking in the text by Abbott, the one we used for 118A and part of 118B. And I might not have assigned this exercise, or maybe you did it, maybe not. But I just want to show you that it's there, and it's in the exercises. So this is sort of part of the inverse function theorem. So it's this one is starting you from the assumption that a function is one-to-one. And then it's telling you about, knowing that the function is injective on a certain region, it's telling you about the derivative of the inverse. So if the derivative of the inverse is going to be a linear approximation to the inverse, and how will that be related to the derivative of f, which is a linear approximation of f? It'll be the inverse linear map, right? Like if you have a linear map that approximates the behavior of f somewhere, then it sort of makes sense that the inverse of that linear map, as a linear map, will be an approximation to the inverse of f, if f has an inverse. And that's kind of what this is saying. 1 over this is how you would invert sort of a 1-by-1 matrix, right? Okay, so that previous exercise from Abbott that I showed you was about, what you can do when you know the function is injective, what you can say about the derivative of the inverse then. And here's a function that's here's an exercise from, this is on page 161, which is more like the inverse function theorem in spirit. This one is having you assume that the derivative is an invertible linear map. That just means not zero for a 1-by-1 matrix or a linear map from R to R. And then you can show that f must be injective. And you can see this came up right after you learn about the mean value theorem. So those kinds of ideas are needed. Okay, so you have sort of, possibly, if you've seen these exercises or worked them out, you've sort of seen the inverse function theorem in one dimension. But it's a lot more complicated in higher dimensions. So let's think about what it would mean to apply the inverse function theorem to a particular situation, say where you have a function maybe from R2 to R2. So it could be from any open subset of R2, but let's just say it's from R2 to R2. That would be a function of two variables, so let's call them x and y, and it would have two components. So maybe we can call those components f1 and f2. f1 of x and y and f2 of x and y. And, suppose f is a C1 function, continuously differentiable, and suppose you had a particular point, like x naught, y naught, in the domain, which for simplicity I'm just making that be R2 here. Suppose you had a particular point where f prime at that point, which is going to be a linear map from R2 to R2, is invertible. Then, just from this linear map being invertible, so from information about the derivative at the point x naught, y naught, you can conclude that there is some neighborhood u of x naught, y naught, such that if you restrict f to u, then that's invertible. So the inverse function theorem says a few other things. It also says, the image of that set is open, and it says that when you look at that inverse, that it's itself a C1 function. But mainly I want to focus on this, because this is the part that, for me at least, sticks with me. This is the part that I remember. This is the part that I think gives it the name inverse function theorem. So there's this neighborhood u of the point x naught, y naught, where f restricted to u would be invertible. So the inverse could be given a name, like g. Maybe I do want to give a name to the image of u, so let me call that v. And the inverse function theorem also can arrange it so that v is open. So then if I say g is what I'm going to call f restricted to u, then g is going to be a map from v to u. And that means g is also a function of two variables with two components. So let me not call the inputs to g x and y, let me call them u and v. Or that's not so good since I have capital U and capital V. Maybe I'll call them a and b. That's also not so good since a is used for something else in the inverse function theorem. How about z and w? G of z and w has two components, g1 of z and w and g2 of z and w. And, oh, sorry, I meant to say define g to be the inverse here. The inverse of f restricted to u. So then, what we have is that if you ever want to solve an equation like z equals f1 xy, w equals f2 xy, say you want to solve this equation, then you can, as long as z and w live in v. So this is a system of equations. And the fact that g is the inverse of f in u tells you that if you want to solve the equations z equals this, which could be some expression involving x and y, w equals this expression involving x and y, then you're guaranteed that you can do it. And what the inverse function theorem does is give you this guarantee. As long as you can show that this is a linear map, maybe write it as a matrix, look at the determinant, as long as you can show that this linear map is invertible. So how is it that it's telling you that you can solve this system of equations? Well, it's saying as long as z and w are, or the point zw is in V, we can apply g to it. So we can do g zw. And since g is the inverse of f, if I do f of g of zw, then I should get zw back, right? So that, in other words, writing things kind of vertically and in terms of components, that's telling me zw equals f1 of g1 zw, g2 zw, and f2 g1 zw, g2 zw. Of course, this is on the right hand side here. This is what it means to say f of g of zw, right? So the inverse function theorem is telling you that you can solve this system of equations. So how to put this? So where did we start in this development here? We started with the system of equations, which is the information sort of contained in this function f of x, y, two equations with two variables. And we had this one like center point that we were focusing on. So this one, two tuple, x naught, y naught. And while u will be a neighborhood of x naught, y naught, in the end here, v will be a neighborhood of the image under f of x naught, y naught. And what we're saying is, if you can prove that this derivative here is an invertible linear map, then near to, here's R2, here's x naught, y naught, here's another copy of R2, here's, let's call them z naught, w naught, which is what I'm calling the image under f of x naught, y naught. F goes this way, right? And what we're saying is, if you're near enough to here, then the equation can be solved. You can go back. This is u and this is v. So the inverse function theorem is about solving systems of equations and getting a guarantee about the solution as a function that also has nice differentiability properties. Okay, so that's what we will study next.